This is our lesson on the scalar equation of a plane, the second of our lessons in Unit 9. So again, last time we talked about how to even think about a plane, what's a way to define a plane, and how could we use a vector equation to specify one. Today we're learning a different type of equation that specifies a plane. In a lot of ways it's easier, but of course you want to be able to translate between the two different types. After this, you can see we're going to try to intersect a line and a plane, and then we're going to concentrate on trying to intersect multiple planes. So let's start with the idea of the scalar equation of a plane. Now, you would have noticed when we were talking about lines, we had, in three space at least, we had a vector equation, we had a parametric equation, and we had a symmetric equation. And what you would have noticed that the difference between that and two space is that there was no scalar equation. And you may have wondered to yourself, like, what happens if you do ax plus by plus cz plus d equals 0, right? A scalar equation can exist in 3D. It uses, three variables, and we set it equal to 0 the same way we would in 2D. And if we do that, what happens is this. So let's say 3x plus 4y minus 2z plus 1 equals 0. And you'll see that what this actually specifies is not a line, but it specifies a plane. And so this is why you didn't have a scalar equation of a line in 3 dimensions, because when we use a scalar equation, it creates a plane. And you can see, even if I just let z work, if there's a different plane with just z, here's one with just x, right? And so you can sort of start to see that you can create planes using linear equations that contain x, y, and z, and some d value that, okay, so for planes now, we have the vector equation, which we said was a point and two non-collinear vectors. That defines a plane in 3D. We have a second definition today, which is the scalar equation of a plane. And this, we realize, is not a line, but it is a plane. Now, if you remember, in 2D, okay, so in R2, the line ax plus by plus c equals 0 has a normal AB. And what that meant was that if you draw a line in 2D, ax plus by plus c equals 0, just go back and quickly draw that. So let's say 2x minus 6y plus 12 equals 0 creates this straight line. Okay, no big deal. And you can see the a value is a 1 and the b value is a -3. And if I graph that vector 1, -3, it creates a vector which is perpendicular to the line, right? If we trace this vector back, if we draw a -n going this way, and you can see that these meet at exactly 90 degrees. We can verify that, just check. If we just draw a line with that goes through the point 0, 0 and has the direction vector u, creates this line G, and then you can just check the angle between these two lines. And, well, it says 270 because it's drawing the big angle, but of course the little angle I was looking for is the 90. Okay, so a line, right, in 2 space, the line ax plus by plus c has the normal AB. Now the part that's going to be, how this is going to apply to a plane, right, in R3, the plane ax plus by plus cz plus d equals 0 also has a normal ABC. This is a really, really, really important idea. I think, again, if you visualize your piece of paper and you stick a pencil perpendicular to the paper so that the pencil juts. If your paper is lying on your desk, your pencil would point straight up. Every single vector on the plane is perpendicular to that pencil, and that pencil is unique, right? It's a unique vector, at least its direction. Obviously its magnitude is not unique, but its direction is unique in terms of being able to say that every single vector on the plane is perpendicular to it. So what I'll demonstrate that here by drawing the vector n equals 3, 4, negative 2. And when I do that, you can see that that vector, right, it's perfectly perpendicular to the plane. And this is actually a different way to define a plane altogether. You can define a plane using a point in space plus a normal vector, because every single point on that plane is going to be perpendicular to that normal. Every single vector on that plane will be perpendicular to this normal. Let's just quickly show, we'll just change this around a little bit and demonstrate this a little clearer. If we have a slider here, so make a quick slider for A, for B, for C. And let's say AX plus BY plus CZ plus 12 equals 0. I'll just put 12 to specify. So we'll zoom this out so we can see it. Okay, and then what I want to do is I'm going to draw a normal A, B, C. Okay, now the normal is a bit small to see there, but what I want to demonstrate here is that, actually no, it would be better, let's just set this to 0, so make sure it passes through 0, 0, 0. That'll make more sense. Okay, so we can zoom in a bit. So no matter how I change the plane, right, the normal always points directly out from the page, as though if we were staring straight at the plane, the normal would come right out towards us. Right? And A, B, and C can be totally different, and this plane can look quite different, but that normal vector always sticks out from the plane perfectly perpendicular to the surface. So this is a really important idea in terms of another way to define a plane. The other day we came up with, 1 was 3 points, 2 was 1 point and 1 line, as long as the point is not on the line. 3 was 1 point and 2 non-collinear vectors. Okay, we came up with those 3 ways. There's now a 4th way you can define a plane, which is a point and a normal vector. And if you have a point and a normal, that's fully enough information to specify a plane. So you can see their picture here. The plane is represented by pi. The normal points either straight up or straight down. Notice the normal, we don't know what way it's pointing, right? But remember that this normal pointing up and this one pointing down are scalar multiples of one another. And so really they are still the same vector, because if the normal pointing up is ABC, then the normal pointing down is negative A, negative B, negative C. And we kind of know that those are, parallel vectors and thus interchangeable in this context. So a scalar equation passes through a point and has a certain normal, right? And then it becomes pretty easy in order to define what the plane is, right? So let's just quickly show how that would work. So we're going to grab all this text and how we would create the expression here for a plane, knowing what we know. So we know that it has to pass through x1, y1, z1, and it has to have this normal. So any scalar equation must be of the form ax plus by plus cz plus d equals 0. Remember, the rules for a scalar equation is that a, b, and c are integers, and a is non-negative. So, if you see a fraction, then multiply through by the denominator until you get rid of all your denominators. And if a is a negative number, multiply through by -1 to make a positive number. So you can see that if we have a normal a, b, and c, and it passes through x1, y1, z1, therefore, right, A x1 plus B y1 plus C z1 plus D equals 0. Now remember, x1, y1, z1 is a point that you know, which means if you had this equation, the only thing you wouldn't know was D. So you can easily just move D to the other side, and then all the other stuff becomes negative, right? Negative ax1 minus by1 minus c z1. And this is an expression that represents D for any one of our questions. So the point that we're interested in, x, y, z, which is just some new point, it would have to be the case that ax plus by plus cz plus d is equal to 0. And remember, d can be replaced by this here. I'll just move this down. Right? And then again, if you need to factor this, you could always factor this. You could go x minus x1 plus b, y minus y1 plus c, z minus z1 equals 0. And this is another way to write the equation of a plane. I don't know, I mean, sometimes this is useful, but really I would just try and think back to the basic form and fill in points as you need. Now, to get the distance from a point to a plane, okay, this is actually, you should have an intuition about how to do this, because as I told you before, there are only two options in terms of pointing the distance from point to plane. There are only two real formula we have for distance, shortest distances, right? Okay, it always comes back to one of these two things. If there is a unique normal, let's just put this in a chart again. So unique normal or a non-unique normal. Okay, let's think of situations where there's a unique normal. Point to line in 2 space, right? Because in 2 space, of course, there is only one normal. Skew lines in 3 space. Let's just write, we can write underneath this, sorry. N is equal to AB, right? In 2 space, the normal is equal to AB for a line. Skew lines in 3 space, we have N is equal to M cross M2 or M1 cross M2. You cross the 2 direction vectors to create the unique normal in 3 space. For non-unique normals, we have the situation where you have a point to a line in 3 space or distance between parallel lines in 3 space. So those are the two ones that have a non-unique normal. Now in terms of this one, we know the answer is we project. Okay, we project PQ onto the normal. That's going to tell us the distance. For this one, we need to PQ cross M, over magnitude M. And we take the magnitude of the top as well. Okay, so think about your exam. Your exam, you need to know, how to take the distance between objects in 3D. Try to remember this schema here. If you can think of a unique normal, do the projection. If you cannot have a unique normal because there are too many normals or you don't know which one to use, then you use the parallelogram technique. In our case here, for point to plane, what we're going to be, there's a unique normal to a plane, right? The normal is equal to ABC, which is what we just learned. So what we're going to do then to get the distance from point Q to the plane, we are going to take a vector PQ. So again, what does vector PQ? It just simply joins the plane, joins any point to the point we're interested in, which is Q. And then N equals ABC, right? And that's going to be your vector. And then we can simply do the projection formula. And remember your projection formula, just if you don't remember, it's a good one to make sure you have memorized. It's equal to the dot product between your PQ and your normal, and then you divide by the magnitude of the normal. So it just comes down to being able to remember these two formula, and this is the one we'll be using for point to plane in R3.